Hi, everyone, and welcome to a special Saturday evening edition of the Common Lisp Study Group. I'm your host, Ron Vadum with Atlanta Functional Programming. I apologize for the delay to this discussion. Fortunately, I had an engagement that prevented me from actually running this stream at our regularly scheduled time at 1 p.m. Eastern Time. For those of you just beginning to join us in our discussions, welcome. As many of you know, Atlanta Functional Programming is a meetup that dedicates itself to promoting the use of functional programming along with uh, other programming paradigms such as object-oriented programming, logic programming, and so forth. Has a major paradigm to actually design large-scale architectures. We are in need of speakers, so for those of you who are in the Atlanta area and are interested in providing a talk, please feel free to reach out to me. I'm Bugram on Functional Programming Slack channel, as well as Tech 404, which is Atlanta's um, tech community's Slack workspace. Additionally, for those of you who are listening in and are interested in presenting your special library or Lisp project on the Common Lisp Study Group, by all means, reach out to me. I am also a squatter on the Lisp Discord server, along with the two venues that I just previously mentioned. Same handle, Bugram, Bugrum. Feel free to reach out to me with your talk topics, and I'll get them scheduled right away. For those of you who are in the Atlanta area, if many of you are interested in doing an in-person meetup, we are in need of a new home. Our original home at the ATDC, unfortunately, has been unavailable for us for quite some time. So those of you who can provide us suggestions for new houses, feel free to reach out to me or Judd Taylor, um, and the two organizers of this meetup, and we will also schedule in-person talks as well. The last couple of weeks, we've been covering the general problem solver, which is roughly what is covered inside Chapter 4 of PAIP. Today, we are actually going to be covering something new, a new system. This is Eliza, which is one of the first, I would say, systems that dealt with user conversation. Okay. It was a system that was designed to essentially perform dialogue in many ways, but I would also say that in uh, in many respects, although I'm not sure if the author agrees with me on this, um, I would say that Eliza kind of also started off the whole question answer sort of spiel in terms of systems and agents that would allow you to ask a question in natural language, have it parse it, and provide some sort of response. Although Eliza itself was designed to actually dictate and have a common conversation with the user to for the purposes of actually seeing if we could mimic intelligent response as an intelligent conversation on a computer. The way it did this, well, let me just kind of take a step back and also mention a couple of other things. One is Eliza was one of the first of a few systems also that was in this realm that allowed us to ask questions. One Another one that's along this was an early 1960s way of doing question answering for high school algebra called Student. And of course, this is something we're going to dive later on when we start talking about symbolic mathematics. The mathematical system Maxima also was there that allowed one to actually ask questions in a mathematical natural notation, and Maxima's responsibility was to solve it in a variety of ways. And this included many mathematical disciplines, particularly differential integral calculus, although I'm pretty sure later versions adopted many what's it many more mathematical subdisciplines in terms of solving and in terms of providing good representations for performing symbolic computation. Um, Maxima is going to be set aside mainly because of the fact that we're going to be dealing with not necessarily symbolic computation in terms of symbolic mathematics, but Eliza and student-like systems, where they're question answering systems, were particularly important in this realm because they process a natural language, okay, and in particularly plain English, okay. So these systems were not designed to handle other languages, although again, to put this into context for folks who are looking at this was the 1960s at the start of kind of all of this. And to be able to even necessarily have a conversation in one language was a challenge, let alone multiple languages. And we have also other problems there because with the human, you'd have to also mimic some way of doing language identification. So there were multiple challenges that had to be addressed at the time, but this particular thing was one of the main reasons why we're focusing on plain English. All right. Eliza was named after, for many of you who may not have noticed, with the main heroine of the play Pygmalion by George Bernard Shaw, where it was a scullery maid, if I remember correctly, in the story, who was taught to speak proper English by a dedicated teacher. This obviously is a very famous play. I encourage many of you to, if anything, read it on your in your free time because it's a pretty good play and had many knockoffs and, along the ways that were made in Hollywood. But the reason why this is appropriate for this particular program is because if you actually look at what we're going to do, it's trying to create simple sentences from simple words in such a way that a human could be tricked into thinking that it's having a natural conversation. That's kind of what its premise was. I just want to quote here just one thing about uh, Eliza before we start uh, diving into some of the stuff that I'm kind of uh, showing. And that is that Eliza's main thing was uh, to start the ability to kind of dive into a area of how would these kind of conversational systems work, all right? And in many ways, the principal developer, Joseph Weizenbaum, in his 1966 issue of Communications with ACM, I like this quote that was in the book, so I'm just going to just say it up front. Um, Really kind of drove this home into understanding some of these things. And I hope this is going to be a sufficient motivation for other people to look at not just some of these more classical systems that we go through Common Lisp and artificial intelligence, but many other systems that are out there, particularly the transformer architectures that you guys are seeing on a daily basis. And so let me just go ahead and read the quote. In his introduction in a paper that Joseph Weizenbaum wrote to the Communications ACM in the January 1966 issue, according to the book, he said, and I quote, "It is said that to explain is to explain away. This maxim is nowhere so well fulfilled as in the area of computer programming, especially in what is called heuristic programming and artificial intelligence. For in those realms, machines are made to behave in wondrous ways, often succinct to dazzle even the most experienced observer. But once a program is unmasked, once its inner workings are explained in language sufficiently plain to induce understanding, its magic crumbles away. It stands revealed as a mere collection of procedures, each quite comprehensible. The observer says to himself, I could have written that. With that thought, he moves the program in question from the shelf marked intelligent to that reserved for curious, fit to be discussed only with people less enlightened than he. Thus, the object of this paper is to cause such a reevaluation of the program about to be explained. Few programs ever need it more. And I think this quote not just describes Eliza's and his goal for this system, but for many of the systems that we're going to be encountering in this book and many others as we continue our journeys through artificial intelligence programming, because those inner workings sometimes end up becoming limitations when you're trying to deploy some of these systems out into the real world. Um, it's often the case, actually, when you're trying to tailor a particular system, that you may end up having to make some adjustments that, in many respects, often results in a subset of the features being unable to be used in that version of the system being deployed on that device or form factor or whatever you're trying to deploy it to. And by understanding some of those trade offs, you can make the right choices and decisions when you are engineering some of these systems. I hope that makes sense for many of you who are following along. Um, just a moment. Looks like I'm having some technical difficulties. Um, Apologies ahead of time. Now, before I begin our main discussion today on Eliza, one thing I wanted to kind of point out is that originally we were going to be talking about also some of the chapter 4 exercises regarding GPS, but I felt that as we dive into some of these Eliza stuff, we can also cover this conversational piece as well as the exercises from chapter 4 in one fell swoop. Particularly the advanced exercises there. So the agenda today is going to be mainly us looking at some examples with Eliza, try to understand at least some of the early versions that were designed, and honestly pick up a few new things about Common Lisp, that some of which we may have forgotten, and maybe even try and modernize some of the things that we see as we go along. So I thought to begin with, it would be useful to first see a first version of Eliza, and this is actually something that is available to us by just simply loading um, the Eliza program, and we'll probably just go Eliza 1 for the time being. Okay. I'm not sure if this is going to work because I may have restarted. Yeah, I restarted. Okay, give me a second. I, um, okay, let us first restart our Lisp just to clean everything out that we done before. And then let's go ahead and load PAIP. And I think that's okay. Okay, so now we have PAIP loaded into our system. So let's go ahead and run the first Eliza program just to give an indication of what we're actually dealing with. Wait, what am I missing here? Requires is undefined. Oh, right. I forgot that I need to first load up the auxiliary functions. One moment. Aux funds. Okay. What? Oh, sorry. Uh, okay. Let us go into here. Aux funds. MCL load. Okay. Eliza 1. Okay. There we go. So now we have Eliza 1. Let us go and look at Eliza 1. If I remember correctly, if I do this. This. Ooh, right. Okay. So what I have to do is, um, wait a second. Eliza 1, I just loaded it. This should actually, okay. Let's see here. What is the program's name again? That was, oh, yeah, that's what I thought it was. Eliza. Style warning and compilation. Yes, but finished. Even though I loaded Eliza 1. Hold on, what is this? Okay. Let's go ahead and load this guy ourselves by doing this. Okay, Eliza rules was not loaded, so let's go ahead and load this ourselves because this is not loading correctly. Let's do Eliza. Okay. So for some reason, requires, which is part of the auxiliary functions library inside of PAIP, is not actually properly getting loaded into my REPL. So I had to manually load auxiliary functions and Eliza separately myself. And then this should actually kind of work the way we expect it to. The first thing to try out is what does this do? Like typically in ELIZA systems, okay, and I'm saying, and the reason I call them systems is because it's really a family of conversational like systems that follow the same realm as ELIZA. And this includes not necessarily or not even exhaustively systems like student, although students purposes is for a different notion. There are additional complexity in there, mainly in the case of solving algebraic problems, which we're not going to really touch base in this chapter. But there are other systems out there that was created, like there was a system that was created called Perry, um, that mimicked the way Eliza kind of worked, and did the same sort of stuff on this. But you will see here, and I'm pretty sure for the sake of simplicity, I'm going to have to use S expressions because the way core Eliza was written in other places, it was not necessarily written in a way that we would use reader macros. Later on, it was used to use reader macros, but some of the systems that were presented by Norvig in his Lisp repository, for the sake of simplicity, ended up sticking with just S functions. So I mean, sorry, S expressions. So that's way we would be able to actually uh, use the facilities that are already available to us in Common Lisp before we actually um, before we actually go through some of the logic related to uh, uh, of doing some of the pattern matching. Okay, because if you used natural language, creating a natural language prompt, all right, much in the likes of modern systems like GPT and things, which again goes back to traces their kind of interface back to this particular system. The one thing that you would have to do is you have to use reader macros, and reader macros ends up adding more complexity into the actual implementation of Eliza, and it actually hides how Eliza is actually written. So for this is I'm just gonna show you some of the basic stuff. So I'm pretty sure I'm gonna have to use this. Let me just try one thing. I need a vacation. Let's see if this works. No, a I need a vacation. Let's see what happens. And it couldn't parse it, right? Yeah, because it's not a type sequence. That's what I thought. So what we have to do is we need to first do I need a vacation, and you would see that it would look up essentially um, some simple examples on this, and if it can't find an answer that's appropriate, it will end up just dumping nil. All right. um so an example of something that will give you a response for starting a conversation. Now let's look at, we would have to go and look at, let's see, maybe some of these other rules. Okay, let's try a simple hello. Okay. Okay, hello. How do you do? So you can see um, uh, uh, what it does is it'll actually take in and create some of these canned responses. Um, I have, let's try one other example. Let's open up paren, say I have a flat tire, period. See what happens. Nothing. So you can see that this is a very limited, very naive sort of, can you actually figure out some of these canned responses? But the nature of the core of code, or at least the core of what this conversational stuff is there. All right. So we're going to look at this naive implementation just to kind of understand what it kind of do. And what it boils down to is essentially just pattern matching. All right. So I want to, before we start diving into kind of understanding this particular implementation, I want to take a step back and start talking about, well, what facilities are there for pattern matching? Okay. Um, we kind of talked about some of this last time when we were talking about EQL and equal and all that kind of stuff. But so this might be just some review, but it is important when we start talking about writing these kinds of necessary helper functions in designing AI programs on top of Common Lisp, because there is a bunch of stuff, facilities available at your fingertips that you don't necessarily need to write from scratch, nor do you have to actually go to Quick Lisp to go and find a package that may have that facility. All right. So to begin, there is this notion of uh, just normal, like, how would you actually go about and um, substitute something inside of a function. Okay. And so let me just first exit this here, and then let's do, see what happens. um, Types of things. Okay, good. Abort. All right. And that is the sublist function. All right. The sublist function takes in an A list and one or more lists of things that you could provide. That A list could be an association of bindings that you're going to end up leveraging of one or more things, and you can use that to actually go in and substitute, as the name indicates, substitute what's in the car or the first of the dotted pair that's inside of the A list with the cdr or the rest of what's inside of that particular dotted pair. So each of these A lists would look of the form of some binding um, with some value that you want to substitute with, right? So we could say like this is hello and world, and then we can provide different sentences that may have these bindings, okay? Like, oops, sorry, I accidentally, um, hello world, okay, or, um, sorry, x y period, you know, this is just a couple of different examples, and it'll just go ahead and update. Oh, sorry, my apologies. I actually have to do, oh, all right. This is that, and this is that. There we go. What is complaining about? Oh, right. I'm gonna have to put that in a quote, right? I can't put that in a quote. It's we can't use period here. We're gonna have to just say, let me see. Let's can I do period like that? There we go. The reason why I'm escaping it is because of the fact that it is that's a special character inside the common. And hold on, I'm just also I just noticed that I can also do this. There we go. So this sublist thing is very explicit on how it's substituting. So you notice that with the question why bang or the why period, what ended up happening is that it treated that entire thing as a symbol that has to whether or not it's going to actually go in and substitute. But it's pretty useful, allow you to make these structured lists and then later on go in and um, uh, uh, once it's all properly structured, you could use like prink to actually go in and create the list of strings that you then concatenate each other to create these canned responses. All right. Um, but we're going to use this sublist to actually create our canned responses, all right, to actually be able to do this. There are other things also available to you in terms of substitute, like substitute and substitute if not, and all sorts of things. But for now, we're going to focus ourselves on just sublist because sublist actually allows you to make, as you saw, multiple modifications inside of the tree, whereas with substitute and the substitute family of functions, you're actually doing new with old inside of a series. So it's a single assignment. Sorry, it's a single substitution that can be done. Um, this obviously speeds up the performance that would allow you to actually make some of these uh, responses. Um, one second. Uh, do I see? Are there are there any questions on this? Should be pretty straightforward. Okay. Um. So how is Eliza leveraging this substitute, and how is it going to be thing? Well, to begin, what we do is we need to first look for these we need to create these special variables inside of our templated responses, our canned responses. So this way, what we could do is we could parse necessarily a question and then make a meaningful canned response based on what the question looks like. Okay, so some questions or family of questions tend to have a specific structure that where the response is going to be somewhat of the same kind of ilk. All right. Contextually, it may not necessarily make sense. All right. But the sentence will be properly structured that it will look like a proper response. Now, if you ask then, so naturally that means if you ask the right question, um, these kinds of systems will then be able to give you what looks like a smart, very intelligent, thought out response. But what actually happened behind the scenes is it parsed the information that it did, took one of its canned templates, and be able to do simple substitution with what you provided in such a way that it could then just answer the question or use the question's information as part of the actual proper answer that it's going to provide you without doing any sort of thinking whatsoever. All right. And so what we need to do is we need to first look at, um, well, how do we actually create some of these stuff? Well, in the case of what's provided in Eliza's, at least in terms of Norvik's version here, is he created some special notation to determine variables for some of these cans, and so these question X's are his way of checking to see if we have a special variable that's inside of a particular string or can string. All right. And the way you do that is you need to think about, as I'm showing you here on line 13, whether or not we're dealing with symbols. All right. Now recall what symbols are. Okay. A symbol is nothing more than um, a data structure internally to Lisp that contains the name and or a function. So like if you see here and we just say symbol name of X here, we will see that it is the string X, okay? And symbols oftentimes can also have functions associated with them. So if we do symbol function of X, in this case, you can see that nothing is bound to X. All right, X has a function is unbound. But if we ended up using something like, say, looking up a symbol that actually has a function associated with it, say the plus sign, you could see that there is a function attached to this function, this object. So we're leveraging the already built-in Lisp symbols to check to see what we can get with this. So we as part of checking if something is a variable, we need to first check to see if it's a symbol. If it's then a symbol, we then can then grab its symbol name and then make sure that the first element of the symbol name, because what's being returned by a symbol name is a string, is this question mark, and this gives us the ability to now add these kinds of variable bindings inside of our strings. It's pretty straightforward. Um, a naive approach to pattern matching. I don't want to necessarily go with the conned system here that's been provided, just because this is a particularly uh, convoluted example, but we'll build up to it. Okay, it's just a multiple. It's naturally just a multiple extensions. It's just a switch statement that you could use with different ways of actually checking with the patterns. But let's kind of work our way up to it. One naive approach that you could look at is something that we could actually write in, say, our scratch buffer, which is something I've already written earlier, and this is from the book. A pretty naive one that checks to see if something is a variable, or if a pattern is a variable, we then set to true. Otherwise, we then go through and loop through the input and the pattern recursively to check if we have a pattern match. Okay, and the way we do that is we check to see if it's not a pattern, well, whether is the given pattern that we're currently looking at, which is recursively going to be done, is it an atom? If it's an atom, then we can return whether or not they are equal to each other. Otherwise, we go ahead and then run pattern match on the first part of the inputs and then the rest. Okay. Now, naturally, the next thing is well, what is equality going to be done? Well, you could do a simple equal, which is something like this, um, which is the same idea as what pattern matching does, and checks to see if you have equality. But this is what ultimately what equal gives you inside Common Lisp. So there are different forms of equality, and kind of show how this is um, we have to kind of look at three different things, and we've kind of talked about this at some point: EQ, EQL, and equal. And there are different variations of this depending upon whether or not you're talking about string types, uh, I think characters also has a char equal and so forth. But normally you can use these three to all Lisp objects. Those are just more specialized and gives you some optimizations for those types. And I think those are also there for historical reasons, if I'm not mistaken. So if we look at char equals, um, this is there for equality. Now, char equals and string equals are basically equal in its fullest form. It's just EQUAL. All right, and we could just check to see if we, test. And in fact, I don't think this actually works if I'm not mistaken. This will complain. No, it does work. Okay, so this works correctly on Lisp objects. There was one of them that I wasn't sure which one actually would not work. I think it may have been EQL then. Test. Is that complain? Yeah. So what is this difference? So we have to go through this. Equal, as we see here, that's the same as simple equal. So simple equal will do exactly what equal does. It will actually take each element in those two strings. Wait, what did I do? Ooh, right, because I forgot to add this to my buffer. 1 second. Now you can see that this is not going to actually work as we expect it to. And why is that? I think that's an important thing, a question to understand. Um, EQ and EQL deal with Lisp with cons objects at the start of at the start. Okay, so if you actually looked at EQ, you will also notice that this will be nil too as well. Okay. And the reason for that is although the contents are the same, has many no's, each of these is its own Lisp object in memory, which means they get their own pointer effectively, right? It's a const object that's in memory that represents a list of characters. That const object doesn't necessarily match the same const object that you have necessarily in a different location. Okay, so where this becomes useful is where you're actually doing pointer comparisons. So like let's say that you have you know um, a to being test. Okay, and then what you do is you define another b to A. Now, until B is modified, okay, these two are sharing the same structure. So my understanding is A would EQ to B, okay, and that also means A equals to B, okay, EQL to B. And on top of that, the content, since they're both pointing to the same location, this is also true. Okay, all three of them that are true. The other two previous ones will give you an optimization because they're doing a pointer location check rather than actually going through and looping through um, every value in the test string. Um, in fact, I'm not. At least this is my assumption on how equal the last one would actually work because I would think it wouldn't be too smart about it. But uh, it will check the types, make sure that the types are matched, and then go loop it one by one. Whereas these two other things, we'll just check to say, is it the same object in memory? Yes. Okay, return true. Otherwise, return nil. Okay. And now what happens is what would happen if we did set f to be to being true? Okay. What is A now? A is test, B is now foo. Okay. At this point, because we set f to B to be something else, it allocated a new memory and just assigned the pointer to object in there because Lisp recognized that B and A are no longer the same. All right. So it doesn't go and dereference it. It actually creates a new object and stick it into memory. Now, if you do EQAB, these are going to be nil. EQL is going to be nil. Okay. Equal is also going to be nil. Okay. Because we made it into something else. One final thing that I want to mention too as well as part of this is with EQ and EQL is let's go back to B being A. Okay. So now we know that EQ is going to be the same, EQL is going to be the same, okay, and equal is going to be the same, okay. And then let's just simply do B being test, okay. If I'm not mistaken, we've just nilled this, right? So while this might give you true always because we've assigned it, what we effectively have done is we changed it to a new object. So EQ and EQL have been invalidated, but equal is now still technically true. These sorts of things you'll end up recognizing depending upon whether or not you need to do pointer comparisons or whether or not we're doing contents comparisons. In the case of what we need to do here, we're leveraging um, somewhat of a mistake, not mistake, a pointer like comparison. Okay. One second. I just been notified that I forgot to share my screen. Okay. For those who are on my Jitsi channel, uh, uh, can you guys see it? Okay, perfect. Okay, another question for some folks. Uh, this is so for those who are just joining us, this is a special Saturday evening edition of Common Lisp Study Group. I had um, uh, a different time. Normally we do Saturdays 1 to 3 p.m. I unfortunately had something that I need to do. All right. Um, we will. Okay. So let's get back to our next um, thing, which is let me just pull up one more thing regarding EQ before we move on, which is common with EQ versus EQL. Okay. So one more thing about EQ that I forgot to mention is EQL does actually a type check. Whereas so what it does is if the or actually EQL is not just a type check. EQL does uh a value check uh if the arguments that are passed in are of that are not Lisp objects essentially. Okay. Um So in the case of characters and numbers, if you saw earlier, we're dealing with strings. This will mean that we would also actually not check their values. Um, Whereas with EQ, EQ is specifically dealing with um, uh, pointers. So they are the same identical object in memory. So EQL, there is a difference here. That this is something that I'm going to also kind of mention. There are some cases where this would actually spit out kind of what we expected. So so like if you do one way of knowing this is if we did one place where this would happen is if we say A is 3, B is 3. EQ is going to say that A is not equal to B because they're not pointing to the same location. All right, they're not oh, it is okay, they corrected this. Okay. Um because my understanding of it was is they had to be implementation. It wouldn't do a type check there. It should have actually said that okay. Okay, the hyperspec is actually pointing this out. So this is something for folks if are watching, this would be useful to know. EQ on numbers and characters might be true or false depending upon the implementation. But EQL is guaranteed for characters and numbers to always be true or false correctly in terms of they will check their values after checking their implementation. Now, then if EQL is that way for things, what is um, equal give us? That is standard equal, the equal operator. All right. So we have EQ, we have EQL that can actually give us equality to as well. But equal is structural. So it will actually do essentially what EQL does, but it's also looking at structural similarity. So it also can deal with effectively um, Lisp objects. So you could use the same thing to deal with whole like classes if you really wanted to, and as long as you provide, I think, equal object, um, like print object. I thought it was a way to actually, you can actually, if you define a class, like if you define a point with x, y, sorry, I should not have done that, but that's fine. We do make point x equals 5, y equals 6, and we set f(a) to being that, and then we set f(b) to being the same instance, sorry, a different instance. Okay, and we then do equal a b, sorry, b, we'll end up seeing that they are not nil. Okay, but if we do EQL, I think they're also going to be not nil as well. Yeah, they're going to be nil. So they're just being treated as different objects in memory, and that's because their equality don't isn't going to be isn't going to show up here. Um, Now, naturally, since equal and EQL and EQ are all dealing with equality, there's also a predicate equal called equal P that you can use to actually do this too as well. All right, and I think this is equal if they are equal. Right. So this is kind of where you'll get exact their values are going to be actually be compared. So if you need an actual comparison, you'd want to use equal p. Equal may not give you what you expect. EQL could give you what you expect with the basic types, and EQ is essentially checking to see if they're effectively the same pointer, if I'm not mistaken. Although again, on SBCL, this is not entirely true. In SBCL, at least, EQ and EQL would be somewhat similar. Okay, that divergent tour, that little bit of a tangent, was necessary because the fact that when we start talking about pattern matching and we start talking about these equalities and then we talk about substitution in ELIZA, that those two functions and these functions also become a key important thing. Now, if we end up just overriding for the time being this, okay, and we just leverage this in Eliza as it is, okay, you're gonna end up seeing some problems, okay, immediately. If I say hello, it's going to we've essentially broken the Eliza program. So what we'll do is we can actually leverage the pattern matching that is provided by the actual code that but before we do so, there is a couple of things that need to be also brought up. One is um, we've talked about substitution, we talked about variables, and we talked about how to essentially take canned information, which are rules, that we could then substitute canned responses for. Okay, and this is effectively the first version of what Eliza does. So if we go back to Eliza and ignore this for a minute, we're going to touch base on this for just a second because this is going into a more advanced situation. If we effectively look at what Eliza does here is we could construct essentially kind of a set of rules that we could load like a database. Okay, um, where um, if your structure of code matches a several section a piece of this, all right, um, you will see that this will give you some sort of canned responses. So like let's say if instead of hello we say hello Eliza, all right, you could see that it's going to hold on. I messed this. Oh, right, because I messed up uh the the pattern matching. I have to actually go in and correct that. Um, let's do this. Load that up. Okay, so let's go back to loading this up again and say if I say hello Eliza, you'll end up seeing how do you do? Please state your problem. I didn't have to just say hello like I did before. Okay. Now obviously this also means I could also write stuff like I want a car and you get canned responses. And these look like natural responses as you can see, but all it's doing as we just talked about before is that essentially they're looking at the input, checking to see if it follows some sort of structural pattern that you wanted. Like in this case, it's looking for I want in the sentence, and then it's looking for it's providing you a canned response that you could end up leveraging. All right. So um, how now then is these rules being read in. All right, is a useful question. Well, these rules are actually a database that are loaded into um, a data structure, right? A list. Okay, as you can see there, it's effectively just um, a a a type of a list where the car of the first of the list is the pattern, the input pattern that we're looking for, and then the rest of the list is essentially a canned response or set of canned responses that you can leverage. So um, one of the things that you could do is you could use sublists now after reading in that definition and then pick a random choice for an answer, and it will give you what would look like a meaningful response, typically based on that sentence that's usually presented. Just mainly because oftentimes one person could see someone answer the question with that kind of response, and that's where this illusion of intelligence comes in. All right. And by the way, all systems that are like this conversational system, okay, all systems, including even modern day question answering systems, although it will look like that they're giving you very intelligent answers, what they're actually doing is nothing more than an advanced, more complicated version of what I'm showing you here. All right. Um, and that brings me to a very important thing that I want to bring up as we're going through these classical AI systems and comparing them with what we're doing nowadays with um, modern day systems um, using machine learning. Uh, the the difference is the scale and the data that they leveraged. Okay, um, this used a very small data base of canned responses, and we're building up to some of the stuff that they provided. Um, and in some cases, some very small niche cases, these kinds of conversational bots could still be used quite efficiently. But in the case of ChatGPT and in case of systems like even its variations like so Llama or any of the transformer architectures that uses LLMs, their main goal buy-in, their main thing that they could give you is a large database that they've trained on to give you an indexed set of canned responses with high confidence for a particular subset of languages that most a good portion of the people use on a daily basis. They will not give you all the answers in all the situations because they don't have all the data to actually be able to do that. Now, one might argue, well, in that situation, why not just give them all the data? That's where privacy and all this kind of security oriented concerns should come in. Not to mention the secondary side effects related to, like, copyrighted materials and all this kind of stuff, because legally there are some things that need to be addressed. But these types of conversational dialogues in this first system that we're kind of studying kind of bring some of these to light. And I kind of want to kind of bring that up here. And I might actually echo that repeatedly as we go through these other systems. All right. So let's take a look at um, how some of these pattern matching stuff works. And I think this would probably be the last thing that I'll be covering today for the first piece of this. And then we could cover the secondary part of the pattern matching next week as we continue the study. Pattern matching at its heart, at least with respect to what we saw earlier, is an extension of the simple equality stuff that we saw. All right, it's a recursive function that we did, except we would now be leveraging uh, what's it? Cond instead of actual if. Okay. Now remember, cond is you implement actually if had like cond, um, but it is somewhat useful. Then if, because of the fact that you might have multiple branches that you might end up writing, and instead of doing if else all the time, it would be useful to have, well, multiple if forms that are nested. It would be useful to just have them all flattened into a single structure. Now, although the Eliza program, the basic Eliza program that we saw here, provided us with. Let me actually check one more thing. I think the basic Eliza program provided us with. Okay, okay, this is the basic Eliza one, and puts with spaces and all this kind of stuff. Okay, so this is a bigger system. Okay, so let me go back to the previous one. This is the simpler one. Um, the one in this one had a more advanced version of this pattern matching with cond that I don't want to touch base on right now. That's actually dealing with something called segmented pattern matching. The basic pattern matching is actually inside the auxiliaries functions piece that I've been able to actually cover. Um, and this is a pretty simple function. It takes in the pattern and input, and it takes two additional optional things that we haven't really touched base yet, but we will talk about now. And that is bindings and partial bindings. Okay. Without getting into too much details about bindings and partial bindings, the function that you're seeing there is pretty straightforward for folks who have touched Common Lisp. Um, Mainly, we're checking to see if in the base cases, are we dealing with a variable pattern? And if we are, then match the variable with a pattern and the bindings that we're provided. Um, if the pattern and the input are actually equal, we can actually return the bindings that we've already have. Um, if both the pattern and the input are both cons pairs, then what we would have to do is we'd have to actually recursively call the pattern matching function on the rest and the of the patterns and the inputs after calling um, the first call, which is taking the pattern match of the first and inputs and the second of the inputs and the bindings. Okay. So the main thing to focus here is on two things. This here, okay, the the main case, and the variable case. When we have a variable, we need to match a variable against a particular binding context, if you will. Okay. Match variable is the next function that we'll cover, but this is just the basic idea. So there are failure cases, obviously, that we'll quickly cover if the bindings in fail are equal to each other, which they could be, then we effectively fail. The default is if it's none of these patterns, then obviously we fail as well. The equal pattern to input will mainly be useful once we're kind of complete, but the recursive patterns and the variable patterns that we saw earlier is the ones that we need to stay focused on. So what does match variable do then? Um, well, what match variable does is it first it itself is going to check to see if the value in the bindings that we currently have matches the actual input that we provided. And if it does, then we can go and return the bindings. Otherwise, we fail. Okay. Um, and if we fail, then if not the binding, then what ends up happening is we extend the bindings and then we return to as well. Okay. The binding is nothing more than an object that contains the variable that we're trying to use and the value. And we have a couple of obvious things that we're creating, but effectively what it is it's going to create a an a list of variables with the associated bindings associated with that particular variable. Okay, so how does this actually look? I think is important to kind of check out. Okay, let's say that you have here. Let's do this. I'm gonna blow this up a little so I can actually get out. I know there's probably a quit somehow in Eliza, but I haven't actually gone through and figured that out yet. Um, but the basic pattern matching idea is kind of like this. You have pattern match, okay? You have your input pattern, okay? Let's say like I need a question mark X, and then you provided a full sentence. I need a vacation. And what it does is it extracts this information and it returns for this variable in this structure, this is the actual binding to it. And it does this by, as you can see, a quick parse of the sentence structure until it hits an exact match with the location. It's basically positional. Um, Naturally, this basic things will give you the ability to actually create a series of uh, canned responses very, very quickly. But the idea is the same. Once you've actually construct this binding list and you return the set of bindings, then you can use those bindings in your rules that we've saw earlier, and it will actually um, construct responses for you. Okay. There are a couple of things uh, in the case of the basic version of Eliza that I may as well just cover, which is that at least this is based on my coverage of this basic example as I was trying to understand this myself. And that is, well, how do you provide this interface to the user? Well, this is pretty simple. I don't know if many of you have seen this. You can actually, um, uh, oh, wait, did I forget to? No, I actually, this is what I forgot to mention. Okay, let's go to this piece. I forgot to mention one more thing before we start talking about the user interface. Um, this uh, use Eliza rules function that's used in this top level function. Okay, one, we could print Eliza the way we saw in order for it to dump. Then what we could do is we could call this use function to actually read in the input that's being passed in. Again, has an X expression. It flattens out the response that's being returned by use Eliza rules. And then it will then write it out and pretty print it for you. Um, what use Eliza rules is doing is essentially it's calling the pattern matching on the rule pattern that's provided with the actual input that you've given to figure out if we have, using a simple search, a potentially canned response that we could ask the user. And if there is such a result, okay, um, which as you can see is provided by doing result in the fail. What we then do is we substitute the result with a random response from the actual rule. So you'll get a list of potential canned responses, and then what you would do is you can call um, uh, sublist on essentially the result that you provided, and use that to actually go in and construct your sentence. So there are two additional functions here that I need to cover. Random element, we've actually covered it before, I believe. We've covered it before in past talks. I would encourage you to go look at our past discussions on random element. It's just a pretty simple check to see if, based on the list, um, to figure out a response. But switch viewpoint is effectively trying to change the tone of the sentence from being like an affirmative, like if I say I, it'll use you, um, and it'll switch it up based on the notion of the actual text, and it does it pretty simply, as you can see here, by doing another um, sublist conversion to be able to construct these sentences. Okay, a lot of this stuff is quite amazing if you actually go and start looking at this. So this makes it then saying, well, shit, we can actually then create these canned responses pretty quickly by having enough of a structured word base, okay, and sentences that we could then use as a basis to actually construct some of these responses, which I at least found fascinating. I thought it was pretty interesting thing to do. Now, naturally, this was very limiting, and one thing the book actually even brought up early on is the fact that uh, Eliza, for what it's worth, clearly showed its limitations when they actually put it up against its own. So I think they have an example of Eliza conversing with Perry, the other dialogue system that I mentioned, a conversation system that I mentioned. And it was clear from the responses that they didn't understand the context in which they were speaking to each other. And as a result, that kind of flew in the face of Eliza being quote unquote intelligent. Um, so this is a basic overview of Eliza. All right. I hope I kind of stretch this across. There's a couple things that we can actually even do today um, with this information. One of which is that we can actually go and um, construct first, from a user standpoint, a proper interface on top of, say, named read tables to be able to construct natural sentences with periods and things. That would require us to actually go in and actually change the Lisp reader a little bit to actually go and allow us to write natural text to the prompt when we are writing it out. We've actually covered this before of modifying the prompt when we were talking about named read tables. You don't necessarily need named read tables, but the named read tables library would come to your rescue in this context because you could then keep track of different types of syntaxes representing different types of readers for to provide you different types of responses. So that is one option. The other one is we can actually go in and change the also the as we understand more about the pattern matching structure, we should try and experiment with different types of patterns and different types of storage routines to actually go and create these kinds of canned responses. I'm going to actually stop here for today just because there's still a lot more to go. 5.3 is talking about segment pattern matching, but I think I've covered quite a this this is a quite of an involved chapter, and I don't want to mess it up. I'm going to open the floor to questions and general discussion. I Okay, if there aren't any questions, then next week we're going to be covering 5.3 a little bit more in detail, um, and maybe even 5.4, just to give people a heads up. Um, and we will start going through some of these more exercises and more experiments with Eliza, with using the basic program that Norvik provided as a template as we design some of this stuff. Um, Okay, there was a question for folks on Jitsi. I'm just kind of waiting. It looks like there's a bit of a lag between my presentation and what's being shown on YouTube Live. So I'm just having it catch up a little bit. Okay, one final call for questions and or general discussion. All right, ladies and gentlemen, we have come to the end of today's episode. I appreciate those of you for sticking around for our discussion. Uh, like I said, I apologize for those of you in the East Coast for the late evening um, special episode. But starting next week, we will be back at our regularly scheduled time on Saturdays from 1 o'clock to 3 o'clock in the afternoon. Um, and for those of you who are available between 1 and 3 next week, I hope to see you guys next week. Thank you for joining. Bye.